Section 7.1 is about polynomial functions. Specifically, we're going to talk about polynomials that have only one variable. We're not going to get into too many two-variable polynomial functions. The degree of a polynomial is the greatest exponent of the variable. So you want to find the variable with the largest exponent, and that's the degree of the polynomial. And then a leading coefficient is the coefficient of the term with the highest degree. So whichever term goes first in descending order, the number that comes in front of that variable is called the leading coefficient. Here we have a table that lists many kinds of polynomials and some information about them. If you have just a number by itself, that's called a constant. The degree of this is 0 because there is no variable, and the leading coefficient is 9. If you have a polynomial that's linear, it has a single variable with a first degree, which is why the degree here is 1, and the leading coefficient is also a 1 because there's a 1 in front of the x. A polynomial called a quadratic has a squared term. In this case, the degree is 2, and the leading coefficient is 3. A polynomial called a cubic has a x cubed, or a variable cubed. The degree here is 3, and the leading coefficient is 4. There are no other special names, but here's the general form for any kind of polynomial function that you can see. They have leading coefficients, and they have exponents that go down or are listed in descending order. Here we're asked to find the degree and the leading coefficient of these, and if they're not a polynomial, to explain why. Well, this one is a polynomial. The highest exponent is a 4, so we'll say the degree is 4. The leading coefficient is the number that comes in front of the first term, the highest exponent term, so the leading coefficient is a 7. This example has two variables, so this is not a polynomial because you can't have an x and a y if you're going to have a polynomial with a single variable. This example down here looks pretty good, except for 1 over x is really an x to the negative first power, and you cannot have negative exponents in polynomials. So this is actually not a polynomial function. In our last example, you see this fraction, and it's in the coefficient, so it's okay. You're not dividing by a variable like in the last example. The only problem with this is it's not in descending order. So I'm going to rewrite it. So now we can see the highest degree is 5, and the leading coefficient is the number in front of this term, which would be a negative 1. This key concept is the definition of a polynomial function. It might be difficult for you to understand, but basically it just says that a polynomial function exists with a degree of n. The degree is the highest exponent on the x term, or whatever the variable is. It has coefficients that it labels a sub 0, a sub 1, a sub 2, and so on. And so you see an example here. N, which would be the degree of this polynomial, is a 2, and then a sub 0 is the first coefficient of a 4, a sub 1 is negative 3, and a sub 2 is a 2. So that helps us define polynomials. Now let's take a look at this polynomial function here and see if we can find out how to simplify and see if we can find out these two values. So we're looking for p of 4, and since p of x is all this, we take the x and replace it with a 4. So 4 cubed is 64, 4 squared is 16, and 16 times 4 is 64 again, and then that's minus 20. 64 and 64 is 128, minus 20 is 108. So p of 4 is 108. P of a squared, I'm going to take and plug in the a squared any place I see an x. So I have an a squared, and then that's cubed. 4 times a squared, and then that is squared because the x is being squared, and since the x gets replaced with an a squared, we square it again. And then 5 times x gets replaced with an a squared. So a to the 6th plus 4a to the 4th minus 5a squared. None of those are like terms, so they can't be combined. So that's as simple as that can go. This example is a little complicated, so you want to take it a piece at a time. Let's start with the function q. Q of x equals x squared plus 3x plus 4. And over here we're asked to find q of a plus 1 minus 2 times q of a. I'll start by just finding out what q of a plus 1 is. So let's examine that. For every x, I'm going to put an a plus 1. Now this is a square of a sum, which gives me a perfect square trinomial of a squared plus 2a plus 1. I'll distribute this 3 here. So 3a plus 3, and we have the 4 sitting on the back. Now we'll simplify with the a squared. We'll combine 2a and 3a to give us 5a. And then 1 plus 3 plus 4 is 8. So that's what q of a plus 1 is. Now I'm going to go over here and find out what q of a is. And that means take all the x's and replace them with a's. So this trinomial is what q of a is. So now I'm going to take and see what q of a plus 1, which I know is a squared plus 5a plus 8, minus 2 times q of a, which is a squared plus 3a plus 4. Now I'm going to simplify this, distributing the negative 2, so we'll rewrite the beginning. So here I'll have negative 2a squared, then minus 6a, and minus 8. Now I'll collect like terms. Here's 1a squared minus 2a squared is negative 1a squared. Positive 5a minus 6a is a negative a, and 8 minus 8 will cancel. So my final solution is negative a squared minus a. Here I'm going to try to clarify for you the relationship between the degree of a polynomial function and the maximum number of times the graph intersects the x-axis. So if you have a polynomial function that has a degree of 0, then it intersects the x-axis in 0 places. Well, how about a linear function? Here's a line. It intersects the x-axis in 1 place, and the degree is 1. Over here is a quadratic function. Well, quadratic functions have degrees of 2, and how many times do they intersect the x-axis? They intersect twice. You're seeing the pattern here. A degree of 3, a cubic function, intersects the x-axis in 3 places. Degree of 4, 1, 2, 3, 4, and finally a degree of 5. So that shows us there's a relationship between the degree of a function and how many times it crosses the x-axis. Now there's also a relationship between the leading coefficient and what happens at the end of the function. If you notice, these functions that are even, the 2 and the 4, they eventually both go up in the air, both ends go up in the air. But these functions that are odd, 3 and 5 and 1, one of them goes up, one of them goes down. This graphic here should clarify that a little bit. This is the end behavior of a polynomial function. Now what this means is f of x, which means the function goes to positive infinity. That's what this symbol means. And this symbol is negative infinity. So as the x's go negative, the function goes positive, and you see that here on the left side. The x's go to the negative direction, but the function itself goes up in the positive direction. On the right side, as the x's go positive, as they go to the right, the function itself goes positive. That happens when the degree is even and the leading coefficient is positive. When the degree is odd and the leading coefficient is positive, then as x goes positive, the function goes up, and as x goes negative, the function goes down. An example would be x cubed. If the degree is even and the coefficient is negative, then it's an upside down parabola. As x goes negative, then the function goes down, and as x goes positive, the function goes down. And the last one, if the degree is odd and the coefficient is negative, then as x goes negative, then the function goes positive, and as x goes positive, then the function goes negative. So here are some examples. We're going to look at them and try to describe them a little bit. First, we want to describe the end behavior. This one, the function, we call that f of x. The function approaches negative infinity. That's because it goes down to the left as the x's approach what? As the x's approach negative infinity because they also go to the left. On the other side, the right side, the function approaches negative infinity again because it goes down as the x's approach positive infinity because as the x's get bigger, the function goes down. So this is the end behavior, a description of what happens on the ends. Now determine whether it's an odd degree or an even degree function. Well, because both ends go in the same direction, it's going to have an even degree. And the last thing says state the number of real zeros. There are 2 real zeros because the function is going to touch in 2 places. Our next example, describe the end behavior. So the function approaches negative infinity as the x's approach negative infinity also. And the function approaches positive infinity because it goes up on the right hand side as the x's approach positive infinity. Because one end goes up and one end goes down, that means it has to have an odd degree. And the number of zeros is 1. Last example,